Hey everyone, today we will finally introduce the term entropy into the course. We will also be looking at a number of equations relating to entropy and how these equations and entropy itself relate to the second law of thermodynamics. Now, the term entropy is actually quite difficult to define. On a basic level, and one that is adequate for the scope of these videos, entropy is seen as a measure through which we can quantitatively define the inability of a process to convert thermal energy into work. So if you look back at the second law of thermodynamics, entropy is a way of quantifying the capability of a process to go in a certain direction. Now, the way entropy quantifies this inability to convert thermal energy into work is not through individual values, such as, say, 5.22 kilojoules per kilogram Kelvin, but rather through the difference in entropy, so say S2 minus S1, and the difference between these two points in the process will provide us a measure through which we can determine whether or not it violates the second law of thermodynamics. So let us say process 1-2 is a compression of a piston cylinder arrangement, and at state 1 it's over here, and at state 2 it is over here. So therefore, if we want to find and let's say that this situation is irreversible, so let's say that there's some friction on the sides here. If you want to see, for example, determine the change of entropy, we just look at the entropy at this state and the entropy at that state, and with regards to that, we can determine whether or not it is a process that is actually viable in real life. So now the derivations of the equation we'll be using with regards to entropy and the second law of thermodynamics are actually quite complicated and complex. As such, if understanding exactly where we get these equations interests you, there are many sources on the internet or in print that will walk you right through it. However, as this would take too much time here, and as my videos are more focused towards examples and questions, it is going to be omitted. Now, the equation that most of us use is the following balance equation for closed systems. That is, S2 minus S1 is going to equal to the integral between state 1 and state 2 of del Q on T at the boundary plus sigma. What this has already been defined as a change in entropy. This is the del Q on T is termed as the entropy transferred, and the term sigma is what we call the entropy generated. All of these are going to be in the kilojoules per kilogram Kelvin that the entropy itself is measured in. Now this quantity over here, the entropy generated, is actually what embodies the second law of thermodynamics. Recall that the second law of thermodynamics refers to a system's ability, and more importantly, its inability to move in a certain direction. This entropy generated term is what will tell us whether or not a process is possible or impossible with regards to the second law of thermodynamics. So by the second law of thermodynamics, this entropy generated must either be equal to or greater than 0. If it is less than 0, that means that the process cannot exist, as the path undertaken will be impossible. If you want to also look at open systems, this is our equation here, which is actually very similar to the closed systems, except this time we have our mass flow rates due to the fact that the boundary is no longer impervious to mass flow rate. And the only other things that will change is that this will be in a rate basis, so it will be kilojoules per kilogram Kelvin seconds, and this will be just the sum of the del Q on T or the temperatures at the boundaries and the heat transfers. For a reversible process, the entropy generated will be 0, but for every other real process, this value will be a positive one. So now, finding the change in entropy, S2 minus S1, for pure substances is actually quite simple. We just find the S value at each state, and we substitute it accordingly. So if you look at our steam table over here, let's say state 1 is over here, S1 and maybe SF, and so it'll be 1.303, etc, etc, etc. And the equality equations are valid, just like what you see before, so it will be SF plus X, Sg minus SF. However, for the ideal gases, we need to have a certain set equations, and they will not find us the exact value of S at a state, rather they will find us the differences. So you can look at the internet or anywhere else to find the derivations of these, but S2 minus S1 is equal to CV, a natural log of T2 on T1, plus the gas constant natural log of V2 on V1, and another equation that is actually exactly the same, however this time we'll be using Cp and P. So what will determine whether or not you use this S2 minus S1 is when you have the volume values but not the pressure, and likewise if you have the pressure values but not the volume values, you use this one. It generally goes by a case-by-case basis. A lot of the time, say for example if it's an isobaric system, then this equation will be easier because since it's isobaric, P2 will equal to P1, so this whole term will be cancelled out, so you only really need to find that one term there to find the change in entropy. So what does this entropy have to do with engineering processes and systems? Engineering systems are subject to a host of irreversibilities, and as such, entropy generation, that is our sigma value that we found before, is a great way to determine the efficiency of our thermodynamic systems. So the greater the irreversibilities, and hence the greater the sigma, the lower the efficiency will be. So as engineers, we need to find ways to reduce or minimize the entropy generated to make better thermodynamic machines and systems.
Cut study time with concise video summaries by top students. Visit spoonfeedme.com to view more free videos in this course and hundreds of others.